Good morning to one and all. Myself Naga Jyothi, working as an assistant professor in Department of ECE. So in the last lectures we have discussed about the time response analysis, in which we have discussed two different types of analysis, transient analysis as well as a steady state analysis. So in this lecture I'm going to detail a description about the concept of stability. So the outline of the presentation is concept of stability. What is meant by stable system? When you'll be saying a control system is said to be a stable system, and how to find out whether the given system is a stable, unstable, or marginally stable. And depending upon the expressions, whether it may be in time domain or in the Laplace domain, from that we can directly say whether the system is stable or unstable. So coming to the first one, so let us discuss about what is the meaning of general meaning of a stability. So here, if we observe these figures, the first figure A represents that it is in a stationary position. So it is nothing but called as a stable system. Similarly, if you observe the second figure, whenever you are keeping this cone in a particular position, it is in the same position until you are giving an external force. Means it is not moving to a particular point, it is nothing but called as a neutral position. But if you observe the third figure, it cannot able to fix that at that particular point, so such a systems is nothing but called as unstable system. So if we observe all these cases, in the first figure the stability itself indicates that there is no movement, as well as it will be in the fixed position. But whereas in case of the second one, neutral, based on the application of the external force, there is a movement of that position of that object. Coming to the third one, it will not be in that position even if you didn't apply the force, or even if you apply the force, means it is not in a particular position which you have kept, so that is nothing but called as unstable. So, in case of a control system, the complete control system judgment can be given by using a concept called as stability. So, if we are giving an input for a particular system, there will be a response from that system. That response is nothing but, in general meaning, we'll be calling it as an output of a system. So, whatever expectation is there, the system may reach to the expectation or may not reach to the expectation. The difference between the actual value and the desired value is nothing but called as an error. So in case of a control system, basically the stability depends upon the location of the poles. So what is meant by a pole and what is meant by zeros, already we have discussed in the introduction part, but let me review just within a example. So let me take, I'm taking an open loop transfer function. The open loop transfer function is represented with a g of s. Let me assume that this is nothing but s by s plus 2 into s plus 4. Now, this is an open loop transfer function. But in order to find out the stability, the first thing is we need to convert this open loop transfer function into a closed loop transfer function. So, in case of a closed loop transfer function, what we are doing, we are having an expression that 1 plus g of s into h of s equal to 0 is nothing but called as a characteristic equation. Or in other words, I can say that the shortcut method is, in order to find out the closed loop transfer function, numerator by numerator plus denominator. This numerator plus denominator part is called as a characteristic equation. So if we are equating the characteristic equation to 0, whatever the things which we are getting, that is nothing but called as a transfer function of a closed loop. So here the first step is, from the given equation we need to find out what is meant by the equating the numerator part to 0 is the roots which you are getting in the numerator part are called as the zeros of the system. Whatever the roots which you are getting for the denominator part, if you are equating to 0, it is called as the poles of the system. So in zeros of, if you take this example, so I can write down this as s plus 2 into s plus 4 s divided by s. So in the numerator part, I am keeping s equal to 0. So there is one 0 present which is at s equal to 0. But if you equate the denominator part to 0, here I'll be getting 3. One is at s equal to 0, other one is s equal to minus 2, and the other one is at minus 4. So from this expression, I can say that there is one 0, that 0 is present at the origin, and there is another pole which is present at the minus 2 as well as a minus 4. So depending upon the location of the poles, I can say whether the system is stable or not. Or in other words, I can say the stability of the concept in such a way that I'll be taking I'll be giving some sort of input for a system and I'll be getting some output. So if the output response can be measurable both in minimum values as well as maximum. So if you observe the first figure, in this figure, as your time is tending to infinity, as t tends to infinity, the amplitude of the signal is reaching towards a 0, and there is a minimum value which is equivalent to 0, as well as there is a maximum value, that maximum value is some constant value. So this is nothing but called as a stable system. But whereas in this case of neutral system, whatever may be the t value, there is no change at the response of the output, that is nothing but called as a neutral system. But whereas in case of the unstable, as t is tending to infinity, as the time is tending to infinity, we cannot find out the value of the amplitude at infinity point. So we'll be knowing the minimum value, starting value is here constant, but as time is increasing, the amplitude is also increasing, but we don't know till what time it is increasing and how much amount of time it is increasing. So if we are able to find out the minimum as well as maximum value of a particular sort of input, then it is called as bounded. If it is measurable, then it is called as bounded. If you are unable to measure the minimum and maximum values, then it is called as unbounded. So in simple words, we can define the stability in such a way that if a system is bibo itself indicates bounded input, bounded output. So that itself indicates in terms of input also we can able to measure the values of minimum as well as maximum values. Similarly, the output response can also be measurable, then it is called as stable system. So the first definition of a stability is it should satisfy, or if a system is bibo, that is output is measurable as well as input is measurable, then such a system is nothing but called as a stable system. And the other one is asymptotic stability. So if system input is removed from the system, then output of the system is reduced to 0. That itself indicates I am taking a system. For this system, I have given an input at a t1 instant of time, and I got an output at t1 plus delta t of time. But at instant of t2, what I am doing, I am removing this sort of input, and if we are getting the output at t2 plus delta t of time equal to 0, then it is nothing but called as asymptotic stability. Means a smallest variations in the input should also be reflected at the output, is nothing but called as an asymptotic stability. And the third type of stability is an absolute stability. A system is stable for all values of system parameters, is nothing but called as absolute stability. So in order to understand the concept of absolute stability, what we are doing is we are taking an unknown parameter. Let me assume that the unknown parameter is value k. If the whatever may be the value of k, if it is stable, then it is nothing but called as absolute stability. Means even if I keep the value of k at 10 or k as 50, if I'm getting an output which is a measurable quantity, then it is nothing but called as an absolute stability. So in order to understand the concept of relative stability, or when the system is changing from unstable system to a stable system, or stable system to a unstable system, that comparison of variation of the stability is nothing but called as a relative stability. So how much fast the system is going to be respond for a particular type of input is nothing but called as measurable, which is nothing but a relative stability. In general, the relative stability can be measured by using some parameters called as damping ratio, gain margin, and phase margin. And in order to understand this gain margin and phase margin concept, we'll be discussing all these things in terms of the frequency plots, that is nothing but either it may be a Bode plot, Nyquist plot, or polar plot. But in this unit, in we are going to just understand whether the given system is stable or unstable. If it is unstable, or if the some part of the system is stable and some part of the system is unstable, what must be the maximum value of k for which the system may be stable? So here what I mean to say over here is, as we know that the complete stability of a system depends on by drawing in the S plane. That is, in general, we are representing S is equivalent to sigma plus j omega. So here the real axis is nothing but a sigma part and the imaginary axis is nothing but a j omega part. So if all, as I told you just now, as complete stability of the system depends only on the poles of the system, but it does not depends upon the zeros of the system. So if we take the characteristic equation, if all the poles are lying to the left half of the S plane, then such a systems are called as a stable system. If the poles are lying to the right half of the S plane, then it is nothing but called as an unstable system. And if the poles are on imaginary axis, let me take that. The characteristic equation is S into S plus 2 into S plus 4. So in this case, there are three poles. The three poles are present at 0, minus 2, minus 4. So this is 0, this is minus 2, and this is minus 4. As all the three poles are present at the left half of the S plane, this system is said to be a stable system. Let me assume that I am taking the other more part, which is nothing but S by S minus 2. So here there is 1 0, that 0 is present at the origin, and there is a other pole which is present at the right side, that is at point 2. So as one pole is located to the right side, then system is said to be what? Unstable. If there are n number of poles, even at least one pole is present to the right side, then it is nothing but called as an unstable system. So the same thing, if the roots of the characteristic equation are lying to the negative half of the S plane, then the system is said to be a stable system. Or if some of the roots of the equation are lying on the imaginary axis, then the system is said to be a marginally stable. And if there are positive values, and if the positive values itself indicates those are lying which side, those are lying to the right side. If the poles are lying to the right side, then the system is said to be unstable. And there is other more condition for that instability. As I told you, if there are roots on the imaginary axis, if there are repeated roots on the imaginary, means on the same point, if I am having more than one pole on the imaginary axis, then only the system, then also the system is said to be unstable system. So in simple words, if the roots are not repeating on the imaginary axis, then it is marginally stable. If the roots are repeating on the imaginary axis, then the system is said to be unstable. So we are classifying this stability. One is if the roots are to the right side, unstable. If the roots are to the left side it is absolutely stable if the roots are on the imaginary axis. So here this represents there are roots on the imaginary axis. If the roots are on the imaginary axis, we need to consider whether there are repeated roots or not repeated roots. So on the imaginary axis, this classification is of two types. If the roots are repeated itself indicates unstable. Non-repetition of roots. Non-repetition of roots itself indicates the system is said to be stable. This is all about the concept of stability. So in order to understand the concept of stability, we'll be using a concept called as Routh array. So by using Routh array, or it is also called as Routh-Hurwitz criteria, by using this Routh-Hurwitz criteria, we can say that whether the system is stable, unstable, or marginally stable. So in order to understand this, there are some steps to be followed. The first step is we need to construct the Routh array. So first step is we need to construct the Routh array. I'll tell you how to construct the Routh array. After construction of the Routh array, we need to find out how many number of poles are lying to the right side or how many poles are lying to the left side. This can be done by observing the first column of the Routh array. So let me take an example, the characteristic equation. So in this case, directly in the question itself, they have given the characteristic equation and we need to find out the system stability. If you observe here, the highest power of S is nothing but the characteristic equation is S power 4 plus 4s cube plus 16s square plus 10s plus 6 equal to 0. The first condition is the necessary and sufficient conditions for the Routh stability is all the power S powers which are there, it should be all the terms should be present. So the here highest power of S is 4. After 4 there should be a term related to 3, 2, 1 as well as 0. So the necessary and sufficient condition is in the given expression not even a single coefficient term should be missed. And the other thing is whatever the signs which are there all should be of same sign. So the first thing is the here in the given question the highest power of S is 4. So I'll be constructing the Routh array. The Routh array can be constructed in such a way that the first two rows of the Routh array can be taken by considering into the characteristic equation. So the here highest power of S is 4. So I am writing S power 4. As 4 is an even, in the first row I should have even coefficients. And the second row should be S cube. So the first two rows of Routh array can be constructed from the given expression. So S power 4 coefficient is 1. So I am writing 1. After 4, what is the next even coefficient? 2. So I am writing the coefficient for S square is 16. Similarly, after S square, the coefficient S power 0. What is S power 0? 6. Similarly, the S cube coefficient is 4. S power 1 coefficient is 10. And this is 0. Or in simple words, first write down S power 4 followed by S cube. S square, S power 1. S 0. And let me assume that this is S power 4 and S power 3. So the first two rows of Routh array can be taken into the consideration by taking the given expression only. I need to calculate what S square. In order to calculate S square, please observe here. The thing is you need to multiply these two. 4 into 6. 4 into 16 minus 10 into 1 divided by always the division is the first number itself which is nothing but 4. So 16 4 64 minus 10 by 4 which I'll be getting it as 54 by 4. So S square coefficient is what? 54 by 4. Similarly, if I want to write down this, I need to multiply 4 into 6, 24, minus 0 into 1, 0. So 24 minus 0 is 24 divided by 4. 24 divided by 4, which is equivalent to 6. As I don't have any term over here, this will be 0. And similarly, in order to calculate this s power 1, I need to multiply same procedure, 54 by 4 into 10 minus 6 into 4, 24. So 54 into 10, which is nothing but 540 by 4 minus 24 divided by 54 by 4. Or in simple, I can say that this 54 by 4 can be written as 14, 4 3 is 12, 2. So 13.5. So this can be written as 13.5. So 13.5 into 10 is 135. 135 minus 24. 135 minus 24 divided by 4, which is nothing but 1114 by 4. In order to write down this, 13.5 minus 0 divide minus 0 into 4 divide anything, that will be getting it as 0. And s power 0, 1114 into 6 minus 0 by 0. So you'll be getting 6. So whatever may be the simplification, this is how to construct the route array. After construction of the route array, we need to observe the first column of route array. So here s power 4 is having a positive value, which is 1. S cube is also 4. So if we observe the first column of route array, all are having the same signs. Means it is plus, 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 plus and plus. As there are no sign changes, that itself indicates system is said to be stable, because in the first column of route array, it doesn't have any sign changes. The number of sign changes are 0. So in this, how many roots will be getting? 4 roots. All the 4 roots are lying to which side? All the 4 roots are lying to the left half of the S plane. So the system is said to be stable. So this is how to calculate the route array. So same procedure. In this case, the highest power of S is 4. So from the question, I'll be calculating the first, writing the first 2 rows. S power 4 is 4 coefficient. S cube coefficient is 8. 2, 10, 3. In order to write down S square, what is the procedure? 8 into 2, 16. Minus 40 by 8. So here I'll be getting minus 24 by 8, which is equivalent to minus 3. In order to write down here, 8 into 3, 24. 24 minus 0, 0 by 8. That itself indicates 3. S power 1. Just cross multiplication. Minus 30 minus 24 by minus 3. It becomes minus 54 by minus 3. Or minus will get cancelled. So I will be getting 54 by 3. And this is anyhow 0. S power 0 is multiplication of these two divided by this. So 3. So if you observe here, this is plus, plus, minus, plus, plus. Plus 2 plus, plus 2 minus. So 1 change. Minus 2 plus, second change. So as there are 2 sign changes, that itself indicates 2 roots are on right side. So total how many roots are there? 4 roots. Among 4 roots, 2 are right side. So how many are left over? Remaining are 2. So 2 will be on left side. So as I told you previously, if at least one root is in the right side, system is said to be unstable. This is how to calculate the stability by using the Routh's array. Similarly, if you observe here, the only change between these two cases is you previously you don't have any unknown value. Here you are having an unknown value. So in order to write down this unknown value, s cube is 1, s square is 3, 7, k. Unknown parameter can be written as same thing. So this can be written as 21 minus k by 3 and this is 0. S power 0 is 21 minus k by 3 into k by this. So I'll be getting only k. So in order to make this system as stable, this is already we know this is positive, this is positive. So it should also be positive, it should also be positive. So k should be greater than 0. This is from s power 0. From s power 1, 21 minus k by 3 should be greater than 0. So if you take this 21 minus k greater than 0 or 21 greater than k, or it can also be write down k less than 21. So 0 less than k less than 21. So if the value of k is in between 0 and 21, the system is said to be stable. If the value of k is greater than 21, the system is said to be unstable. Thank you.